Alright, so here's our setup. We have a cube, and we would like to paint each face of the cube a color, and I have 3 colors to choose from. How many distinct ways can I paint the cube? The word distinct there is key, right? Because if I just have this cube and I don't care about distinct, I don't care about worrying about repeats, well, if there's 3 colors, I have 3 options for what to paint face F, times 3 options for face T, times 3 for R, times 3 for L, times 3 for U, times 3 for B, and I have 3 to 6 different ways I could paint this cube. But some of those are repeated, right? Because I've labeled the faces here just to make it easy to describe. But in real life, these faces aren't labeled. This block is a solid cube. Each side looks just the same in terms of size. So if I paint the top red and all the other sides white, that's the same as painting the front red and all the rest white. Because I could turn one into the other way of rotation. So I need to know how many distinct ways, how many ways where I take into account that there's some rotation and don't count those repeats. Sounds like a lot of casework. I'm going to show a way to do it that's systematic. It still feels a little bit like casework, but it's not. It's very elegant. I don't know. It's kind of elegant way to do it. Okay, so first off, we need to think about all the different ways we could rotate this cube in space. Forgetting about color, just how many ways we could rotate it in space. Right, we could take this cube and we could spin it about an axis of rotation that passes through the center of T and U. And we could rotate it 90 degrees clockwise about that axis of rotation. I'm just going to call it like TU. Or we could rotate 180 degrees about TU. Or we could rotate 270 degrees about TU. Or there are 2 other axis rotations that pass through the face of a cube. Each of these 9 rotations is going to result in a different orientation of the cube in space. There are other ways I could rotate it. I don't have to pass through this axis rotation. I don't have to use an axis rotation that passes through the center of the faces. I could use an axis rotation that goes right along a main diagonal. For instance, this diagonal that connects the vertex 2 and vertex 8. I could take it, and that one, my options are rotating 120 degrees or 240 degrees. I could either rotate it so 6 goes to where 3 is, or I could rotate it so 6 goes all the way to where 1 is. So I could do a rotation of 120 degrees about 2.8, or a rotation of 240 degrees about 2.8, where 2.8 describes that axis rotation. And how many ways can I make a diagonal like that? Well, there's 8 vertices, so there's 4 pairs of vertices, so there's 4 different diagonal pass-through vertex axis rotations I could do like that. And these 8 different ways I could rotate are different than the ones I did in orange before. I'm still listing distinct ways I could rotate this to a new state in a new orientation of this cube in space. There's another axis rotation I could do that I haven't listed. I could do an axis rotation that passes through the midpoints of opposite edges. So say I look at the midpoint of this side 2, 6, and I look at the midpoint of this side 4, 8, and I do a line that goes right through those midpoints, and I rotate 180 degrees about that line. I don't know what to call that line, but I do a 180 degree rotation about this edge, mid-edge axis. And I didn't even say what name, I didn't give it a name, but I could at least count how many of them there are. There are 12 edges, 6 pairs of edges, so 6 different axes that go through mid-edge that I could do. 6 of these. It's okay that I didn't bother even giving them a name. I'm just trying to list how many different ways I could turn this cube in space. Let's see how many I'm up to. I have 9 in orange, plus 8 in light blue, that's 17, plus 6 in green, that's 23. Are there really 23 different ways I could orient this cube in space? Actually, there's 24. I didn't really need to list them all. I could find the 24 different ways pretty easily, right? I have, there's 6 different faces. I have 6 options of which face to put in front. Once I fix one face to be in front, there's 4. I could spin it, so there's 4 different options for what's on top. So there's 24 different cubes. I listed 23 of them, but the 24th is leave it exactly how it is. Don't rotate. That gives me the 24th way I could orient this cube in space. At this point in the video, I had some technical issues, so we can watch those as I say. What I have to do now is I could start thinking about coloring the cube, but instead of coloring faces of the cube, what I'm going to think about is coloring orbits of the cube. As I repeatedly make some of these moves, the sides kind of line up in these little groups, these convenient groups, and I think about coloring each of those groups. For instance, let's take that first one. If I take a rotation 9 degrees about the axis of rotation that goes through face T and the center of face U, if I repeatedly do that move, then I'm going to see the faces kind of form these orbits. Face T is going to stay exactly where it is. It's not going to go anywhere. It's just going to kind of spin in place. Face R is going to go to where face F is. Face F goes to where face L is. L goes to where face B is, and B goes to where R is. And they just kind of spin in place like that, forming a little cycle. And where I'll face U is just going to spin in place. There's 3 different separate orbits of faces that never cross. So in a sense, I have 3 different, if I want to color this cycle that I make, there's 3 different spots to color in. There's the top cycle, the middle cycle, and the bottom cycle. There are 3 different things to color. I have 3 options for each thing to color. So I could color this 3 to the 3rd different ways. As opposed to if I did an 180 degree rotation, if I did an 180 degree rotation, T would still be staying where it is. Meanwhile, face F would go to where face B is, and B would go to where face F is. Face R would go to where L is, and L will go to where R is. And U would stay in place. So then, if I do an 180 degree rotation over and over again, I would notice that I have, this time, these 4 little cycles that never overlap with each other. T, F and B, R and L, and U. So there's 4 different things to color in this case. I have 4 things, 3 options for each thing. 3 of the 4th different ways I could color these 4 cycles. So all the ones with 9 degrees here, I'm going to have 3 of the 3rd ways to color it. All the ones with 180, I'm going to have 3 of the 4th. I hope I'm making clear how I'm coming up with these. I'll do another example. Let's say I'm rotating through one of my diagonal ones. The axis rotation that goes through 2 and 8. If I did that, what happens to my faces? What kind of cycles do they form? Well, rotating through this over and over again, F would go to where R is, R would go to where U is, and U would go to where F is. That's the three corners that are the three faces that are touching R2 would all swap places with each other. Meanwhile, the three faces touching vertex 8 would all swap places with each other. I would have face T, L, and B would form their own cycle. These two different cycles, I want to each assign a color to. I have 3 options for each one, so 3 for the first cycle, 3 for the second, gives me 3 squared different options overall. All of these 120-degree rotations. I have 3 squared options. All the 240 ones are just 120 in the other direction. If I spun 180 degrees about a mid-edge axis, no face would be fixed. Each face would swap with another face, but then swap right back if I do the rotation again. Each face is going to be part of a little cycle of 2. Out of the 8 faces, they would form these 4 little cycles. So I would have coloring each cycle a different color. 4 cycles, each one I have 3 options. I have 3 times 3 times 3 times 3 different ways to color it. And the only one I haven't discussed is if I don't rotate. Well, if I don't rotate, and I think about how many little cycles are formed, well, each T doesn't go anywhere. It's its own little thing. B doesn't go anywhere. It's its own little thing. R doesn't go anywhere. It's its own little thing. I have 6 different faces that aren't going to form any sort of cycles. They're each their own little cycle of 1. So I have 3 to the 6 different ways, different cycles. This seems like really bizarre. Why do I care math? But now's when the magic happens. I average together all these numbers I've written in dark blue, and I average it together. There's 24 of them, so I'm going to do 1 over 24 times 3 to the 6 plus 1, 2, 3, 4, 5 plus 6 3 to the 3's plus 1, 2, 3 3 to the 4's plus 8 3 squares, and lastly 6 3 to the 4's. If I average those all together, I get 57. If at the start of this problem you told me that my answer was going to come out to odd, I wouldn't have believed you. I would have been like 6 faces. There's no way it's going to come out to an odd number. That's crazy. 57 is the number of ways I could paint all the faces of the cube, where for each face I have 3 options. Neat. I don't know if this makes sense. I'm going to find a video on YouTube that does it better than I do, but I already made this, so maybe it'll be useful.